The ocean is not merely a vast body of water covering our planet. It is the largest mechanical battery on Earth. Every single second, waves crash against our shores with pulses of raw force, an untapped energy reserve exceeding 30,000 terawatt-hours per year. To put that number into perspective, this amount surpasses the total electricity generated by all of humanity in 2023. We are living next to an immense energy goldmine, yet for decades we have stared at it from a distance, unwilling or unable to touch it. While we successfully learned how to harvest sunlight through silicon and tame the wind with colossal turbines, the ocean remained something else entirely, a graveyard of engineering dreams. Sunken prototypes, budgets dissolved into salt water, startups erased from memory, swallowed beneath the waves. This failure was never due to a lack of ambition, it was because the ocean is a chemically and mechanically hostile environment. And then, in 2023, something unexpected happened. A Swedish company called CorPower deployed its floating devices directly into the heart of violent storms. These buoys endured waves reaching 60 feet in height, and they didn't just survive, they continued delivering clean electricity to the grid as if nothing extraordinary were happening. The secret was not resisting the waves, it was resonating with them. Through intelligent engineering inspired by the rhythm of the human heartbeat, CorPower achieved something that had eluded engineers for decades. We're now standing at a pivotal moment in history. Either this marks the birth of the blue economy, or we accept that the ocean will remain a beast humanity can never truly tame. But this raises a critical question. Why did the giants who came before CorPower fail so catastrophically? And what is the deadly orbital motion that destroyed billions of dollars in ocean energy investments? In 2024, the world celebrated a milestone. Renewable energy reached 30% of global electricity generation. Solar, wind, and hydropower carried the majority of that burden. Yet the ocean, despite covering 70% of the planet's surface, still contributes less than 1%. Looking only at the coastlines of the United States, the National Renewable Energy Laboratory, NREL, estimates that capturing wave energy just 10 miles offshore could generate 770 terawatt-hours per year. That is enough to power 71 million homes and supply 1/5 of the entire U.S. electricity demand. Move slightly farther into deeper waters, and the ocean alone could provide 1/3 of the energy needs of the world's sole superpower. So where is the bottleneck? The answer lies in what engineers bitterly call unfriendly physics. In wind or hydropower systems, energy flows in a relatively stable direction, pushing blades consistently one way. The ocean is different. Its motion is chaotic. Imagine a rubber duck floating on the surface of a wave. It does not move forward. Instead, it follows a looping path, rising with the crest, drifting slightly forward, then sinking and being pulled backward with the trough. This circular, irregular motion, known as orbital motion, is the engineer's nightmare. Converting these chaotic water loops into smooth, continuous rotational motion capable of generating electricity is profoundly difficult. We have seen ambitious projects reduced to wreckage. The Australian company Ocean Links lost its massive generators off the coast. Portugal's famous Pelemus project, nicknamed the Sea Snake and once hailed as the future of wave energy, collapsed both financially and technically. The ocean does not only destroy machines mechanically, it attacks them chemically through salt and corrosion, and biologically as marine organisms grow over every exposed surface. Any design that hopes to succeed must solve an almost impossible equation. It must be delicate enough to extract energy from gentle waves, yet strong enough not to shatter when a winter storm unleashes its full fury. But what if the solution was never about making machines stronger? What if the real breakthrough came from teaching them how to adjust their rhythm, the same way modern computer processors dynamically tune their performance through software? This is where the true game-changing innovation enters the story. Modern designs, such as EEL Energy's undulating membrane or CorPower's adaptive buoys, no longer attempt to confront waves like rigid concrete walls. Instead, they rely on advanced control systems that allow the device to oscillate at a frequency perfectly matched to the incoming wave. This phenomenon is known as mechanical resonance. And when resonance is achieved, something remarkable happens. The system stops fighting the ocean and begins amplifying it. The amount of energy extracted increases not incrementally, but by several multiples. Yet the real advantage of wave energy is not just its sheer power, it is its timing. One of the greatest weaknesses of solar and wind energy is intermittency. The sun sets, the wind can fall silent for days. A study from Stanford University revealed a striking reality. Offshore winds in California can stop producing energy for up to 1,000 hours per year. The ocean, by contrast, rarely rests. Periods of low wave activity typically do not exceed 200 hours annually. Even more compelling is what happens when wave energy is combined with offshore wind within a single grid. In that scenario, total downtime shrinks to just 100 hours per year. Waves are the perfect companion to solar power. During winter, when sunlight is weakest and solar panels lose efficiency, wave energy reaches its annual peak. Along the west coast of the United States, the energy available in ocean waves during winter is 4 times greater than in summer. This consistency dramatically reduces our dependence on massive, expensive battery storage systems. What we are talking about is a reliable baseload energy source, one capable of stabilizing the grid and delivering power without interruption. So, if this technology is so close to ideal, what is the financial barrier that turns placing a wave generator beside a wind turbine into the deal of a lifetime, capable of saving billions of dollars? The largest obstacle to wave energy has always been capital cost. Laying an undersea power cable and anchoring it securely to the ocean floor is astronomically expensive. But a solution is now emerging on the horizon: co-location. Instead of building standalone wave farms, the new strategy integrates wave energy converters directly into existing offshore wind farms. Consider the advantages: a single environmental permit, a single subsea power cable, shared maintenance vessels, a unified operations team managing both systems. According to estimates from Wave Energy Scotland, integrating a 100-megawatt wave farm with a 500-megawatt offshore wind farm can reduce the wave project's capital costs by up to 40%. In a world where land is increasingly contested, the ocean offers vast, untapped real estate. And if costs continue to fall at the current pace, experts predict that pairing wind and wave energy could reduce the total energy capacity required for a zero-emissions grid by 17% by the year 2050, simply because we would no longer need to build redundant backup power plants to compensate for weather variability. Wave energy today is experiencing the same moment solar power faced in the 1990s, a promising technology burdened by high costs and widespread skepticism. But this time, the context is different. We now possess artificial intelligence, corrosion-resistant materials, and an escalating climate crisis that transforms this sea of broken dreams into a necessity for survival. So the question remains: are we ready to turn every wave that strikes our shores into an electrical pulse that lights our cities? The answer is already forming on the horizon, where machines no longer battle the ocean, but dance with it.